So the 5 steps we're going to be following is establishing the non-alternative. And it says set the level of significance, but that's usually given in the problem. The test statistic we're going to do with one samples is either a z-test or a t-test. So just like with confidence intervals, if we know the population standard deviation, we're going to use a z-test. If we don't know it, we're going to use a t-test. We're going to determine the critical region and a p-value, and then we're going to make a decision. Either we reject the null or we do not reject the null. And again, in Newton it says fail to reject the null. And then we're going to do our conclusion. So these are the 5 steps I'm going to have you do on the weekly test, the exams, and the final. However, Newton may ask you bits and pieces of this. So you may want to practice when you're doing this just to first write down these 5 steps and then go back and answer the Newton questions. Okay, so number 2 is I'm going to show you here some formulas for the test statistic. The formula when sigma is known is a z-test, and this is the formula for the z-test statistic. And when sigma is unknown, this is the formula for the t-test statistic. Okay. We're going to determine our critical region based on whether it's a right-tailed, left-tailed, or two-tailed test. And we use the table to determine these critical regions. And I'll show you here in the examples. And then the p-value, basically the critical region and p-value are 2 different ways that we determine the decision, but they actually align with each other. Okay, if the p-value is less than or equal to alpha, we reject the null, and if it's not, then we fail to reject the null. Okay, so here's the formulas for a z-test and a t-test, and then down here is the formulas if we're dealing with proportions. So just like with the confidence intervals, when we deal with one sample, we can have one sample for when we're testing on the mu, whether we know sigma or don't know sigma. And if we're testing for the proportion, we have a what's called a one prop z-test on our calculator. Okay? All right, let's look at an example. I think it'll make more sense when you have the whole example here. Okay, a mechanic believes that people travel more than 5,000 miles between oil changes. A random sample of 18 cars getting an oil change has a mean distance of 5,075 miles since having an oil change. Assume the population standard deviation is known to be 225 miles. At the alpha 0.1 level of significance, test the claim. All right, so let's state the non-alternative here. So we do H with a subscript of 0 with these colons here, and then the alternative is H with a subscript of A. Okay, so what I usually say is, okay, put in the alternative first. Test the claim. Well, what is the claim? The mechanic believes, this is his claim, that people travel more than 5,000 miles. So in my alternative here, I'm testing that mu is greater than 5,000 miles. Okay, then I go back and put the null in. The null is the complement of that, less than or equal to 5,000 miles. Okay, so that's my null and alternative. Those are my hypotheses. Now my test statistic is based on the information that's given. So I'm going to write down my information that's given here. I know n is 18, right? And then it tells me in this sample, the mean is 5,075. So that's x bar they're giving me. Okay, and then it goes on to say, assume the population standard deviation is 225. So that's telling me sigma, right? Population standard deviation. So when I know the population standard deviation, okay, when sigma is known, I use a z-test, right? Okay, rather than using the formulas, I'm going to go straight to using your calculator here. Okay, just like we did with confidence intervals, we're going to go to stat, over to test. Now with confidence intervals, we went down to z interval, t interval. Well, now we're going to use these initial ones here. These are for hypothesis testing. So we have z-test, t-test, then we have 2 sample z-test, 2 sample t-test, 1 prop z-test, and 2 prop. So just like with confidence intervals, okay? Since we know our population standard deviation, we're going to use the z-test. Okay, the statistics are given, so I'm going to input what I know. Now, This says mu with a subscript of 0. That means, what did you assume in your null hypothesis? Well, in the null hypothesis, I assume that mu is less than or equal to 5,000. The equals always go in the null hypothesis. So it's what I'm assuming here is in the null is 5,000. Okay? My sigma that is given is 225. My x bar is 5,075. My sample size is 18. And you can see I'm just typing over what was there. Okay, now this is asking us, okay, what's your alternative? Is it not equal to that value of 5,000? When it says mu naught, it means what you put here. Not equal to 5,000? Is it less than 5,000? Is it greater than 5,000? Okay, looking at ours here, alternative is greater than 5,000. So we arrow here and then hit enter when it's flashing over that. Okay. Now you can either hit calculate or draw, and explain draw in a little bit here. We hit enter and it's going to calculate your z-test statistic, and then it's giving you here what's called a p-value. So let's first write down what our z-test statistic is. It's 1.41. Okay, what was that? 1.41, right? Now I'm going to go ahead and just write down what the calculator gave me for the p-value. And what I usually do, instead of writing p because of the proportion, even though the calculator says it this way, I write down p-value 0.0786. 0.0786. Okay, so when we do the critical region then, there's two ways we determine how we make our decision here. Remember, our decision is either we reject the null or do not reject the null. Okay, so when we do the critical region, what we're going to do is draw a picture of what's called our rejection region. And that is based on whether it's right-tailed, left-tailed, or two-tailed. Okay, so we look at the alternative, and this shows us it's a right-tailed test, right? Because it points to the right. Just look at the inequality like an arrow. Okay, that means our rejection region, our critical region, is in the right tail. Okay, so what we're looking at is we're finding this as a breaking point. Okay, I'm going to call this Z with the subscript of C, Z critical, just like we did in confidence intervals. Okay, and Newton will give you a table. So if I look this up on the table, it should give me a value of 1.28. Okay, so basically what this is saying in the critical region is if my test statistic falls in this area, this is called my rejection region, or sometimes we call it critical region, okay, then that means if the test statistic falls in here, then then I reject. If it doesn't, if it falls over here somewhere, that's my non-rejection region, okay? So what we do is we take and we draw, where does my test statistic fall? Well, I know on a standard normal this is 0, right? So where does 1.41 fall in relation to 1.28? Well, it's greater than that, so it's pretty close to it, but it's somewhere right here, right? My z equals 1.41. Well, that actually fell inside my rejection region. So I'm just going to skip down here. I'm going to do this in two parts. So my decision based on the critical region is that I reject the null hypothesis. Are you with me? Looking at my test statistic, it falls within the rejection region. Therefore, I reject the null. Okay, that's how the critical region method works. Okay, the p-value then, basically the p-value tells us, sorry about that, we're going to reject the null if our p-value is less than or equal to alpha. Well, we got to look back in our problem here. Alpha was 0.10. All right, so looking at my p-value is 0.0786. The question, is that less than or equal to 0.10? Yes, it is. So if we say yes, then we reject the null. Okay? If we had said no, then we do not reject the null. Does this make sense? Okay, so let me explain what the p-value is here. Our p-value is actually this area under the curve right here to the right of our test statistic. Okay, so back when we do in the normal distribution, we could find this p-value from the table by looking up 1.41, subtracting from 1, that will give us this area right here, which is our p-value. And because this area is smaller than my rejection region, that's why we reject if it's smaller than alpha. Alpha is actually equal to this area under the curve here. Make sense? Okay, we'll do another example here in a second. So our conclusion then is at the 10% level of significance, we say what we say here is either we do have enough statistical evidence or we do not have enough statistical evidence. And this just depends on whether reject, kind of like the guilty or not guilty, right? When you were not guilty, you did not have enough evidence. When you're guilty, you did. So when we reject, we do have enough evidence. When we do not or fail to reject, we do not have enough evidence. Kind of the knots go together. Okay, so we did reject. So we do have enough statistical evidence to conclude that, and we got to look back at the problem now. What were we testing? We were testing the claim that people travel more than 500 miles between oil changes. Okay, so looking for that word that kind of helps us here. That people travel more than that. People travel more than 5,000 miles between oil changes. Okay? All right, we'll do another example here too.